Thanks for joining us today. So this event is brought to you by Data Talks Club, which is a community of people who love data. And we have weekly events. Today is one of such events. If you want to find out more about the events we have, there is a link in the description. So just click on this and you will see all the events we have scheduled for the next few weeks. So we have events like today, which we have usually on Tuesdays, which are more technical with presentation, and we have events on Friday, which are maybe less technical, it's just an interview live podcast. Don't forget to subscribe to our channel if you want to stay up to date with all our videos that we have, and of course join our Slack to talk about all data related things. And during today's presentation, you can ask any question you want. So there is a link, pinned link in the live chat. You just click on this link, you ask any question you want, and we will cover these questions after Max finishes his presentation. So that's all for the introduction. Max, the floor is yours, please.
All right. Thank you so much. Thanks for inviting. Very excited to talk about our journey in building streaming analytics. So let me start introducing myself. My name is Max Lukichev. I've been in the industry for a while. Have a PhD in query optimizations on the databases, and started my career actually as a computer scientist. So I was doing research in this exciting field 20 years back, XML databases, which kind of I don't think you hear anymore. They were replaced by the other type of technology.
Yeah, I've heard about them at university, though.
Yeah, it was a hot topic back then. Yeah. But after that, I jumped on the startup band and been through this. Right now, this is my 5th startup, and the previous were quite successful. All the time I was building SaaS data management platforms, analytics, monitoring, but it was pretty exciting to build everything kind of cloud native, high scale, and so on. The most interesting out of this experience were definitely, I mean, the more relevant to this talk, were from Reltio and SignalFX. Reltio was the data management platform, like with the master data management core, all in cloud, streaming, very high scale, multi-tenancy, and SignalFX was the monitoring platform, infrastructure monitoring, and then it was later acquired by Splunk, so it became part of Splunk. About 6 years ago, I switched to the leadership track, which gave me another
question.
perspective.
Are you sharing your slides right now?
Oh, I thought so.
So I thought maybe it's too long for an introduction without. Yeah, okay, now it's better.
Yeah. You see?
Yes.
Yeah. Yeah, and finally, right now, founder and CTO of Telmai. So we are building the data quality monitoring platform, but again, residing on the same principles of streaming analytics and big data. So in this talk, I want to make it a little bit less theoretical. So and talk more from the personal perspective, like what kind of problems we ran into in our journey building streaming analytics through these multiple companies. When we started, it was very early days. You know, back in 2011, Cassandra was just picking up. You know, I don't know. I remember Kafka was probably there, like very early versions, and same was with Spark, like version 0.9 or something. So there was nothing to pick from. Like there was no good or solid commercial solution. So observing this landscape was also very interesting, and I will cover in this talk. Then I will touch a little bit on the Lambda and kappa architectures. Like a lot of people are wondering, you know, when to use which, what's the benefit, and so on. Again, we'll try to bring it from the personal perspective. Have done both, and you know, wrap it up with like key architectural decisions you will have to make, and some of the alternatives you would like to explore while on this journey. So let's get started. So I will try to stick to the journey from the relative times. It's the most representative because, as I said, like we started early and we were able to observe the landscape as it evolves. So it might be an interesting experience to, again, kind of look back what could have been done differently in modern world, well, modern, like a few years later. But yeah, Reltio itself, it's a cloud data management platform, and it has a master data management in the centerpiece, as a centerpiece. What it means is it streams data from many different sources all into the single platform, and then it cleans the data, unifies the schema, does the deduplication data, which can be related, but come differently from different systems. So there's like very comprehensive merge rules, survivorship rules, like what value, actual attribute value should you take if you have like 5 records merged together, and so on. And imagine this all happening in real time. And at some point, we just needed to build the analytical system for that. So it was the core was pretty solid, built on a good foundation for big data and cloud. It was the first cloud native system of this type back then. The analytic piece was missing. And that's what I was working on. Our big data stack was Cassandra, Elasticsearch, and Spark. As I mentioned, data was in constant motion. Like, it wasn't a batch upload or anything. It was constantly added, merged in the background, updated. And the data was coming at extreme spikes. So it wasn't like the steady flow. For example, like in Signal Effects, we had a huge flow of data, but it was steady. Here it was like extremely spiky, but the volume might not be as high. And finally, multi-tenancy, keeping an eye that tenants or customers who are having huge loads don't affect others. All of this, trying to build an analytical system which kind of respects all of those restrictions, constraints, was a very interesting challenge. Our mindset when we came up to this journey was honestly like buy versus build. So we were never biased to like build everything in-house. But as I said, because there was not much available, we had to build a lot. And later, when the market caught up, we started exploring options to kind of sunset the previous solutions and kind of move to the commercial offerings, just because like it was not the core focus of the company to keep building all those internal infrastructure systems. Let's look a little deeper into the choices we had to make. Very classic decision you try to do when you're tasked about building the real-time or streaming analytics is which architecture to pick. Today, the two most common ones are Lambda and Kappa. There are a few more people bring once in a while. Databricks is trying to establish the concept of Delta architecture right now. Right now, it's still kind of in the forming phase, so it's not as well established what it is. It's more like a marketing term. But let's stick to Lambda and Kappa. The main distinction between them is the structure of the, how to handle the batch. Lambda, on one side, consists of two layers, batch and speed layer or streaming. Batch is obviously like you're getting a lot of data in batch, and it does something. It produces the outputs for the serving layer, and the serving layer is used for querying. And the query is being answered by two layers, batch, the results from both batch and streaming. So both batch and streaming produce data into the serving layer. There are a lot of benefits of doing this way because obviously, like when we're working with very large volumes of data, batch is just much more efficient, and it can do much more comprehensive analytics. But you also want to keep stuff up to date, so that's why you add the speed layer on top. Kappa, on the other hand, trying to simplify that previous approach. So obviously, like batch and speed layer, they're completely different. They can run on very different technologies. So it's double the development or maybe triple the development to just make sure like all the consistency and other stuff is taken care of. Kappa is dealing with just single layer. Let's assume we don't have batch, we have the speed layer, and everything is done by the speed layer. It evolved probably together with the evolution of the message buses like Kafka. And basically, if you need to rebuild something or do like a more historical analysis of the data, you just kind of replay it from the topic. In Reltio, we did the Lambda architecture, something that closely resembles the Lambda. In signal effects, it was much more closer to the kappa architecture. So yeah, I can definitely compare, side by side, benefits and the pros and cons of each. Let's go. Yeah, so for when you build your analytics, one thing to consider, and the first thing you want to consider is the serving layer. Why it is important? Because this is where your queries are coming from, and you need to really analyze the patterns of well, first, how many queries will be coming, what is it, like relatively kind of low frequency of querying, kind of high large scope of queries. Let's say you're processing the huge amounts of data. And to keep it more practical, what we had to build, actually, when the events were streaming, so part of the streaming part and the, I'm sorry, I will rephrase. When we were processing the events, it was updates of the objects. An object can be, let's say, a person. It has multiple attributes: first name, full name, last name, address, whatever. So when it gets merged, it becomes a new entity with completely new attributes, because one piece can be picked up from the one record, another piece can be picked up from another record. And when you want to do analytics on that, you actually have to look through the entire scope of the data. You cannot just take the latest version, because there's a lot of kind of on-fly processing when you assemble the data. This was quite a challenge for us for the serving layer, and that's why we ended up with the Spark, for example, as a serving layer. It's sometimes typical for these layers, but in our case it worked beautiful, because we could write very complex logic at the read time. Now, Spark is not very efficient when you there is a Spark streaming, but there's a lot of challenges if you try to kind of put the stream of events into it, and especially like extremely spiky stuff. So that's why we had to build completely different streaming speed layer from the batch layer. The speed layer, the batch layer was rather classic. We have a Cassandra database, and you just have a Spark job which is reading from the Cassandra database, does all the processing and stores the Parquet files for the serving layer. And this was great to start with, and that's something which very natural in the progress you would do. First, start building the batch layer, and it also serves as a great way of repairing your analytical views. The views that you produced, something went wrong, you have a bug in the code, you screwed up, like not all the events were delivered, you just kind of rebuild it using this logic. But the same approach doesn't really apply when you have streaming, because Parquet files, if you start creating a lot of them, Spark will not be able to handle it very well. They have to be of certain size to be efficient. So there's a lot of challenges with that. And that's why we had to pick our build a completely custom speed layer. We couldn't use Spark streaming for multiple reasons, such as multi-tenancy, for example. We cannot run multiple Spark cluster for every tenant. We had more than 1,000 tenants, and data isolation was a very important security requirement. So with this, my advice would be first start finalizing your batch layer. Once you have done this, you already have your analytical system, which you can operate with some frequencies, and you can start switching to the speed layer. And when you do so, start with the message bus, finalizing the message bus. Some of these decisions here you would have to make is, would you go with the self-hosted or the managed messaging system? In our case, we evaluated Kafka, we evaluated Kinesis, SQS. We ended up with SQS. Why? Because when we really compare the cost model, especially understanding the volume of the data and the size of the objects will be going through the message bus, it turned out that the SQS was just made sense and it was easy for us to work with. Kafka, on the other hand, it's a great system, but it gives a lot of trouble when you operate it at scale. In my experience from relative, from signal effects, the systems which gave the most trouble and had needed the most attention from the team were Cassandra and Kafka. They just require a lot of manpower just to support and keep them running. And also they don't react very well for the spikes. So you either create a huge cluster to handle this, or and then you just burn money when you don't have much load, or you run into troubles. So again, make your choice based on the volume of the data, on the pattern of the data coming. Do you want to go with managed? Do you want to go with a self-hosted? Are you going to be supporting the multi-cloud later? So do you want to have the same solutions for like GCP, AWS, Azure, or are you okay to stick with single cloud? Once you have done this, pick your message consumer architecture. This is another very important thing. In the streaming layer and the speed layer, you will have a pretty robust pipe to deliver the messages, but you also have to be processing them very efficiently. We evaluated here, should we go with the containers, Kubernetes cluster or whatever for the consumer of these messages, or would we go with the serverless like AWS Lambda? And what worked really well for us was the decision to go with Lambda. As I said, that the pattern of the data was so erratic. We could have billions of events processed, let's say, emitted in an hour, and then nothing after that for an hour, 2 hours. So having it's completely unpredictable. You cannot predict when you would have the wave of the events. But we also had to provide a very, not strict SLA, but very firm SLA that no matter what volume of the data was, in few minutes, we have to deliver all of them to the serving layer. It wasn't true real time. I mean, we didn't care. No one cared in my experience about having an analytics, up to a second. People usually tolerate very fine, if you deliver it within a few minutes. But if you can say that, okay, I promise you it will be done in 5 minutes, you have to. And that's why all our logic about having containers and auto-scaling on the containers, it was getting very, very complex, and still was, there was always these corner cases where our logic just wasn't capturing the metrics we were capturing we're not telling correctly about the spikes, the magnitude of the spike. So we were fighting with this logic for a while until we switched to Lambda. And for this data pattern, it turned to be like the beautiful solution. In the Lambda, you wake it up, let's say once a minute, once in a few minutes. It will read everything from the topic. It will split it into multiple lambdas for actual processing, so you can scale. And then it will die. It done its processing, done. And it not only turned out working very well for this spike, so it was able to, very predictably handle all of this within a fixed amount of time. It also was very, very cheap to operate because most of the time the load was very minimal. So we didn't burn any money for just keeping the large cluster. If I remember correctly, our whole spend on the whole deployment for like 1,000 tenants on the Lambda to do this processing was something like $1,500 a month. It was like really nothing comparing to all other components of the architecture. So once you have figured this, the consumer architecture, think about keeping the serving layer, optimized. In our case, our serving layer was really the collection of formatted, certain way or structured certain way Parquet files, not Parquet files, just the files on the S3, and to keep this fast for querying, we had to build a complex logic of compactions. The streaming events, as they were getting to the Lambda, they were dumped very quickly onto S3 as like binary files. The next layer of compaction was concatenating those binary files into the bigger files. So when you read it with Spark, you have much better partitioning. So your Spark plan is much simpler and run faster. You don't have this overhead of having too many partitions, small partitions. And once we have this concatenated files, it went for a daily compaction to translate it into the Parquet files on the day increment. And eventually, once a week, to combine it into even smaller file, the completely compacted like a weekly file. Reason for this was because we were getting a lot of updates to the data. And you don't delete in these storages, right? You just append and put the tombstone for the old for the old object. So obviously, by the end of the day, you would have the storage, which would be like 5-10 times bigger than it would be after compaction when you delete all those tombstones. So as you can imagine, this was a lot of complexity and definitely caused us a lot of expenses on the development and maintenance. However, all of those systems were managed. Everything related to Spark was managed by Databricks. So we were actually running all the Spark jobs on Databricks. There are alternatives, cloud native alternatives. Would you run it on EMR or would you run it on, let's say, in Google on Dataproc? But what turned out is they are really inferior to the Databricks ability to troubleshoot and the comprehensive, management configuration. So it was, even though it was much more expensive option, it was just totally worth it, just to save on the development time and save developers' time. And
maybe I have a few questions. I'm just wondering if we can make it a bit more concrete. So let's say what kind of queries in your particular case you needed to answer? Like maybe we can just come up with some, like it doesn't have to be a real example, maybe just some example.
Sure. Think of it as you want to, first of all, you want to get the data available for analytics. So just to get that, you have to read all the objects from the storage with all their attributes, understand their schema, and create, let's say, data frame for that. And after that, you want to figure out which values should you display on each object, because when again, in our case, the analytics was like to understand which value you display for the first name. There was a policy which could change, which is telling if this is coming from the record which is the most recent, I will pick this value, this first name. Or for example, if it's coming from the record which is more complete, I would pick this value. And all of these things can be happening and are happening at the read time. So there's a lot of complexity. The query itself is complex to even pick the value which would go into the object.
Could you think of an example, like what could be a query? Like, I don't know, how many operations per day, per country do we have, or like what kind of queries you wanted to answer?
Yeah, the final analytics on top of that is let's say you want to build a hierarchy of the objects. You know, our model in reality was a graph, right? So you can have, let's say, companies and their subsidiary companies, which have a relationship between them. Okay, so you want to actually build the hierarchy of these companies. What's the parent company out of this? And you want to roll up, let's say, revenue of all the subsidiaries into the parent company. But also you want to make sure that the attributes on that parent company are also accurate. Like they are like the golden record, so-called golden record, right? So they are, after all the mergers which happened in the background, when this this data came from multiple sources, it was reconciled into the golden record, right? So this is like two layers of complexity. First, like understanding to show the proper values, and the second one is actual analytics on top of this proper values. So you show the accurate, like aggregated data.
So basically, this is like analytics that your customers could run on their data after it was merged. Okay, so it wasn't product analytics to understand how your customers used your product, but was like to give a platform for your customers.
Exactly. And I should have mentioned it in the beginning. Yeah, exactly. It was a platform on which our customers or our partners, development partners, could build a layer of their own analytics.
And
so we had a lot of stuff kind of out of the box, but yeah, it was purely for the platform.
So basically your customers would put their data, then you would find duplicates, merge, and so on. And then on top of this cleaned data, so to say, they could run their own analytics. They could run their own queries using, in this example, since you mentioned serving layer was Spark, right? So they could just use Spark to run their jobs, right?
Exactly. And I will come to that in the next slide. Yes, initially it was the idea they would use Spark to do that. And we just had to build the efficient way of delivering data for the Spark, basically, for the serving layer. And as we proceeded to go with that, our first solution was AWS Native. So we used SQS as a message bus, Lambda as a consumer, S3 as the storage for the serving layer, and Spark for consuming this data and running the queries and serving the results. But as we proceeded, one more requirement started popping up quite often, that a lot of customers said, okay, can you just deliver it to our data warehouse, which happened to be BigQuery. And we thought, okay, definitely we can use our pipeline to deliver this stuff into the BigQuery, but why to cause this complexity if, let's say, in 80% of the cases, our analytics, coming back to your previous question, was, a lot of those things could have been answered by the SQL query. There were still 20% of cases, more advanced cases, high-value cases, where you would need like very complex, comprehensive Spark capabilities to do these roll-ups, more complex logic, even like recursive rollups. But for 80%, you could have the data in the BigQuery and run SQL queries. So BigQuery becomes the serving layer. And instead of kind of building yet another layer after, like to our AWS native solution, and then kind of trying, like from there trying to ship data to BigQuery, we decided to fork it at the very beginning. So we just started sending to two locations, SQS for Amazon customers and the PubSub for these BigQuery users. And that solution turned out to actually pretty well. It simplified a lot the architecture that we had before. So basically, events were entering the PubSub. Then they were consumed by the data flow. And to structure them properly, do a little bit of the augmentation of the data, some small analytical calculations, and then dumping into the BigQuery. That solution actually worked really, really well. And for a lot of customers, we were actually thinking of even not enabling them the original pipeline, because they didn't use that Spark capability for their use cases. So why to have this complexity? So even though kind of BigQuery and this PubSub data for BigQuery is not typical Lambda architecture, I find that it's quite a viable for a lot of cases when you build analytics. So, if you can consider this option, it works really, really well. It had a little bit of problem with, not problem, it wasn't as elastic as SQS and Lambda for the spikes of the data. Data flow scales slightly differently, but it was still good. It was still meeting our requirements. And another one alternative is the Databricks Delta Lake. It's very fresh, or like a few years old. What it's doing is pretty much doing what we've built for the AWS Native. Like it's giving you the access to your data in Spark, like handling all this streaming layer, delivering these events, change logs, and compacting this data over time and so on. So if we were building this, let's say today, we would definitely consider Data Lake. But it wasn't there. It wasn't available when we started.
We have a question about the language, the programming language used for Lambda. I don't know if it actually matters, but yeah, maybe you can tell us a bit more. What did you use for implementing these Lambdas?
Absolutely, we used Java. And more than, we used a lot of kind of very, very heavy jars for Java. I know this is not recommended for Lambda, but this was the only choice for us because there was a lot of logic from the core system which we had to keep in the Lambda. There was a lot of this processing logic, how to assemble the events into the object, and yeah, it worked very well. If you stay within the limits of Lambda, it works very well.
And then I have never used Dataflow, but can you use the same jar in Dataflow, like the same logic?
No.
Oh, you have
Dataflow
to implement it.
It's using Beam's API. So Dataflow is it's more of like alternative to Spark streaming.
Okay.
If you can, it just uses the Beam's API, which itself is not bad, and it works very well for like a very linear pipelines when you do, like, let's say aggregations, but don't do forking, don't do joining or whatever. But the moment the plan gets hairy, it will cause you a lot of trouble.
And for managing these lambdas, did you use something specific, like maybe use serverless, or you just just maybe
timer.
CloudFormation or okay.
Timer? What's it? CloudWatch?
No, I mean like for setting it up, like for managing these lambdas, or you just because
we just had an API through which we were deploying a lot of this stuff, because we were not only deploying Lambda, we were deploying also Spark. So it was like a package going out. So we just developed a very simply internal endpoints. Go deploy it.
Yeah, because we also run a lot of Lambdas, and sometimes it's quite painful to manage all of them and update. And we use Terraform, and it's not ideal for that.
Yeah, 100% agree, and that's why we had to build more of like the programmatic logic for that, like more advanced scripts. Because you're right. Then when the amount of them grows high, that becomes challenging. So the more automation you can, the better.
Thank you.
And finally, just want to summarize some of the things that impressed, something that could have been improved. First of all, I'm a big fan of Databricks. It's expensive, but saved so much time and effort troubleshooting things, comparing to EMR, comparing to Dataproc. It's just totally worth it. Their ability to visualize the plan right away when you kind of run the code on live data, troubleshooting this job, just unmatched in my opinion. They did really, really good job there. BigQuery, best asset in GCP. In fact, in Telma, my current company, we decided to go with GCP purely because of the BigQuery and Data Studio. Our goal was to prototype our analytical system even before we start building the rigid, UI and complex user experience. we decided, okay, we'll just build the Spark engine and we will build the mockup in BigQuery and Data Studio just to understand how it all works. And this is just beautiful, like so little effort to put all this analytics together, try it out, and then once you finalize what you're building, go and build it in a different technology. But BigQuery is just amazing in my opinion. AWS Lambda, again, never gave us a problem, was super cheap to operate, was the best decision we made for the streaming. Wouldn't work very well if you had a lot of like steady flow of the data, but for our data patterns was working really, really well. So something which worked but caused some pain was data flow. Worked really well for simple pipelines, as I mentioned, but is the moment you get more complex logic, the moment you start kind of joining data with itself and just forming something more complex, it's going to cause you more trouble. So at this point, probably think of Spark because Spark has much more lower level controls on the execution. Cassandra and Kafka, despite how great they are, like the most expensive outages and the most butthurt we had from these two things. Elastic was not far from them, but these are the champions. And finally, to wrap it up, what architecture would you pick, Lambda or Kappa? I would put this way: if you can start with building streaming a layer, and you will be fine living for a while with the streaming layer, check yourself. Maybe you don't even need Lambda. So try hard to stick with Kappa because of its complexity. And only if it's too hard and you have the requirements, a lot of batch data coming in, which is not as efficient to process in streaming and whatever, and then consider Lambda. But try to stick with Kappa as you can. That's it. Thank you very much.
Yeah, thanks. I think I missed the part when you talked about Kappa. Was it?
Yeah, it was a little earlier. I didn't speak a lot about the Kappa. I just mentioned that single layer versus two layers.
Mm-hmm.
Kappa, as an example of Kappa, I can give signal effects, for example. What was happening there? Data points which are collected from your infrastructure, let's say CPU, disk space, whatever. They were coming to the API, which will then coming to the Kafka topic, and then from the Kafka topic, the first layer of analytics, it was basically aggregating them at different resolutions. Let's say one minute, 1 hour, 1 day, whatever, and then storing into the serving layer for the actual advanced analytics. And that worked very well for Kappa because there was no batch layer. Everything was coming from the the stream of events. If something happened, it could be replayed, kind of to restore this serving layer. So it was, not probably the canonical Kappa, but the closest to Kappa as possible.
So basically, from what I understood from your presentation is, in Lambda, we have two layers. So we have this batch layer where we basically process data in chunks, right? So like, let's say we run something every hour. And then we have a streaming layer where we use things like SQS or Kafka or something like this, on message bus, where we process the data as we receive it, right? And basically, if you take this Lambda with two different layers, and if you remove batch from this and you just keep the streaming, it kind of gives you Kappa, right?
Okay. Yeah. So it's how it is, right? It's the simplification of Lambda where you don't have to deal with batch anymore because your message bus, the Kafka, can actually be this storage for you to replay this data, right? To reconstruct your serving layer, for example, if you need, or do more advanced analytics once in a while, right? By replaying this data. So it's a simplification of the Lambda. And it is possible because of more advanced topic message bus. which can deliver that.
Yeah. So basically, if you take SQS, which you used as an example, then it won't be possible to use to build kappa on top of it, right?
The SQS would not handle that.
So I guess the key difference here is that in Kafka, you still have the message once you process it, right? In SQS, once the message is processed, it's gone, right? That's
well, I prefer, yes, and I prefer to think of it just separate yourself from the technology itself. I mean, you can do this without any Kafka and SQS, dumping the right log on the file system. But the point is, if you don't have to have this separate batch layer, just don't invest in it. Like, don't do it just for processing. I'm trying to simplify it kind of from the example. Like in Reltio, we had to build the batch layer because we had an existing system. There was a storage in Cassandra, and the moment we had to enable analytics, there was already a lot in that system. So data to that system or from that system was extracted in batch anyway. So we had to have batch no matter what. Like we couldn't just kind of do the streaming because it was putting too much load on the data. Like we cannot stream everything out of the system all the time. So that's why we had to build the batch, because it was just much more efficient and much more easy way to extract data periodically. But if the system was, let's say, we were building the system from the very beginning, we wouldn't do that. We would just kind of stream it and probably keep the data for analytics in kind of write log somewhere in the cheap storage, and then just kind of replay with the single layer within the kappa architecture from the get going. So the Lambda is a great alternative when you have a lot of restrictions on, like, there's an existing system or whatever, like what you can do. Like if you have the full kind of blank list of what you're building, most likely, I would personally go with kappa.
So if I understood correctly, so we have two layers, two distinct layers, but we don't process the same data through these layers. So through batch, we process the data that goes only through batch, right? For streaming, we process only data that for which maybe we need to run analytics. Yeah. Okay.
Yeah. It's just like, imagine you have batch which you can run once a day, but you want to deliver something much faster. It will not be as comprehensive because, in the streaming, you cannot have all the same analytics as in batch. But, at least you deliver these results faster. So you build the second completely separate layer, separate layer.
Okay. Is it does it process the same data as batch, or usually these are like different data sources?
No, it can process the same data as batch. But
so
it can.
Okay. So at the end you kind of duplicate, but you duplicate it because for one use case you want to analyze the data as it comes, and in the other case maybe you want to have a more precise result, and it's okay to wait for a day to actually run this analysis.
Yeah, for example, in the speed layer, let's say you're doing deduplication. Your deduplication of the speed layer will be limited to the time window. In the batch layer, you can have the full historic duplication.
Okay, yeah, thanks.
Unless you build a lot of complexity into the speed layer.
Yeah, you mentioned that Kafka gave you a lot of headache. So what do you think about kinesis? Like, is it better or it's the same?
My personal opinion is, I would go with the managed solution. Again, depends on the, the business. But if it's not your core business, try to go with the managed solution. Again, if it's economically viable, it will give much less headache. Just to put in the perspective, for my teams through multiple companies, I had to keep at least 2-3 engineers watching after Kafka, like when operating at scale.
Okay. Because I guess Kinesis can get expensive, and then it also has the same. Well, you don't need to manage it, but in terms of scaling, you have you basically have the same constraints that you have to think about the number of how it's called partitions, like a number of divisions within the stream in advance, and then this repartitioning is a very expensive operation.
This is this is the problem with these systems, that the whole repartitioning thing, the spikiness, they don't handle very well.
Kinesis has the same problem as okay, but at least you don't need to have a team to manage it, right?
That's exactly the fact. You're just basically like you either pay predictably, like and it also comes back to the CFO question, right? Do you want to pay upfront and the fixed cost, or you will pay as you go, basically?
Okay, or pay also with downtimes.
Yeah. I mean, Amazon can also have downtime.
Yeah, well, they recently had like a massive outage. Something actually, something happened with their kinesis, and then because of that, like the entire region was down. Yeah. So maybe they use Kafka underneath, and yeah, it gave them some problems.
Yep. I mean, same with Kafka. You will have to build a multi-region, parallel Kafkas sometimes. I have seen that, having actually 2 pipelines of Kafka just to, mitigate those, region outages, whatever, like problems in one region.
Yeah. So maybe another question from me is, how can we learn, like, for example, for those who do not necessarily have experience with running these things, how can we learn more about this Lambda and Kappa architecture? Maybe you know a good book or a good talk, a good video, maybe a good course that those who know only basics, like maybe people who know a bit of SQL and stuff like this, like how can they pick up these topics and understand, okay, when to use Lambda, when to use Kappa, what are the moving parts there?
I usually, so a lot of good resources are in fact on AWS. They do a good job describing architectures and even like some real-time examples. There are a lot of solution architects who are kind of making posts about how to build this architecture and that architecture on the AWS stack. So this is one good source. Databricks is pretty good, but keep in mind they will be trying to sell you the Delta Lake. Sometimes GCP is having good resources. I couldn't recommend any other book. I mean, probably just because I didn't like read one. It was more from the practice and experience.
So basically, you learned all these things by just doing.
By doing, and again, talking to like partners at the cloud vendors, what they recommended, how they kind of navigated us. So we had this luxury and interacting very closely with AWS and Google teams in this journey.
Okay, so they basically showed you different options, and this is how.
I can recommend, for example, for GCP, what I like about their model, you actually work not directly with Google, you work with the partner, so a reseller of GCP. So in our case, it is SATA. This is not advertisement, I'm just kind of sharing as a great partner, right? And they actually bring in people. So when we have, let's say, trouble or question how to build something, the architectural question, they actually bring a lot of experts who have done this, who have seen this through a lot of customers who are helping. So consider this as one of the best resources you can. Like having a good partner for your cloud implementation is very important.
Okay. Yeah, we at OLX actually have these solution architects. So probably we should make better use of them. Oh, because I mean, solution architects from AWS, maybe we should talk to them more often.
And another use of them, in fact, if let's say you're building a new product and whatever, they're a great sounding board. so they can give you feedback because they see all this use cases. They see a lot of customers, so they can definitely help you with your product too.
Mm-hmm. Okay, thank you. I don't see any other questions, so maybe we can wrap up. Maybe the last one is if people have questions to you, how can they find you?
Please ping me on LinkedIn, Max, or email max@telm.ai.
Okay. Yeah. Thanks a lot. Thanks for joining us today, and thanks everyone for watching us and asking questions. And yeah, I guess that's it. And have everyone enjoy the rest of your day. Thanks, Max, for joining us.
Thank you so much. Thanks for inviting me. Bye-bye.
Yeah.